Good afternoon, student. Today we will start our second unit, diffraction of light. When the wave come across the obstacles, they bend around the edge of the obstacles. If the dimensions of the obstacles are comparable to the wavelength of the wave, the bending of the wave around the edge here around the edge of an obstacles is called as a diffraction. Here we consider the obstacles A, B, and this is the source of light. When the rays of light is bent across the end of the obstacles, they will form the diffraction pattern. The in figure, the bending of waves around the sharp edge of the obstacles AB. Here, the bending of this is the obstacles and the rays get bent from the edge of these obstacles. The region CD, this region CD on the screen is termed as the geometrical shadow. This is the screen. Due to the bending of the edge of some light can reach the point just below the C and just above the D. Hence the intensity does not fall to 0 below the C and above the C on this screen. It means that when the rays get bent from these obstacles, they will falls on the screen. This is the screen, and this is the say point C. Below that point and the above that point, there is some shadow region here. This is therefore it is called as a geometrical shadow. The bending of light at the sharp edge of the obstacles whose size is comparable to the wavelength of the light is called as a diffraction, and the distribution of the light intensity on the screen is called as a diffraction pattern. When the opening is large compared to the wavelength, here the opening is large compared to the wavelength of the source, the wave do not bend from these obstacles. In general, the diffraction of waves become noticeable only when the size of obstacles is comparable to the wavelength. His size of obstacles is comparable to the wavelength of the source of light, then only we get the interference pattern on the screen. Here are the two types of the diffraction. One is the Fresnel diffraction and other is the Fraunhofer diffraction. The first is the Fresnel diffraction. In this class of diffraction, the source of light or the screen, this is the source of light and the screen, both are at the finite distance from the diffracting obstacles. Here this is the diffracting obstacle, this is the source, and this is the screen. Here in Fresnel diffraction, the distance of the source and the screen is at the finite from these obstacles. The diffraction effect at any point on the screen is due to the expose of the incident wave front and do not due to the wave front blocked by the obstacles. Here we get the diffraction pattern, or here we get the point P. This point P is due to this bending of the rays from that obstacles. The entire analysis of the Fresnel diffraction is based on the Huygens-Fresnel principle. The to observe this Fresnel diffraction effect, no lens is required because this screen and the source is at the finite distance. Therefore there is no need of the lenses or no need of any type of the mirror. Also, this Fresnel diffraction is based on the Huygens-Fresnel principle of the secondary wavelength. The next is the Fraunhofer diffraction. In this case, the source of light and the screen are effectively at the infinite distance from the obstacles. Here, the screen and the source is at the infinite distance from this obstacles. Therefore, there is the need of the lenses. Therefore, there is the need of the lenses. The diffraction pattern can be observed by placing the source of light and the screen in a focal plane of the two convex lens. Here, by placing this source and the screen in the focal plane of the two convex lens, the first lens make the rays of the light parallel. Here, this lens makes the rays of the light parallel, and the second lens which bend the their second lens which is placed behind this aperture or the behind this obstacles are makes the rays parallel for the screen here, and finally they intersect merge on the from the intersection point on the screen at point P. In the laboratory, the Fraunhofer diffraction means this type of diffraction is obtained with the help of spectrometer. The diffracting aperture is placed on the prism table. This is placed on the prism table. The collimator lens render of the rays of light parallels, and telescope receive the parallel rays on its focal plane. This is the Fraunhofer diffraction. The only the difference between this Fresnel diffraction and Fraunhofer diffraction is that here the source and the screen is placed at the finite distance from these obstacles, and here the source and the screen is placed at the infinite distance from these obstacles. Here the lens are required to observe the diffraction. In this case, here there is no need of the lenses to observe the diffraction here. Then the assumptions of the Fresnel diffraction. Here we consider that this Fresnel diffraction is based on the Fresnel theory. Then the assumption for that Fresnel theory is that the diffraction is due to the interference of the secondary wavelength. Here we consider this interference. Here the interference is produced on the screen is due to the secondary wavelength originating from the different point of the primary wavelength. Is this which is blocked by these obstacles. Here we get the interference pattern, and that interference pattern is obtained due to the secondary wavelet which is originating from the primary wavelet, but this is this primary wavelet is bent or cut by these obstacles, and then finally we get the interference pattern on the screen. This is called as the Huygens-Fresnel principle. Again, the second point is that the any wavefront can be divided into the large number of zones or the strip called as a half period zone or the strip. Here, the number of wavefront can be divided into the large number of zones. In the next derivation, we will see there the number of zones. The third point is that the resultant effect at a point P on the screen is sum of the effect of all the secondary wavelet reaching the point P from all the zones. Here, the effect at point P is depends on its distance of the zone and its with respect to point P. Here, zone and the other zone plate and the zone we will see in a next definition. Here, the next is the Fresnel half period zone. We will study here the zone, Fresnel zone. Here is the Fresnel half period zone. Here we consider to find the resultant. Here we consider the number of different zones and having the point P on the screen. Point P on the screen. Here to find the resultant intensity at point P due to the wavefront, the Fresnel has suggested to divide the wavefront. Here we divide the wavefront into the number of half period element or the zones called as a Fresnel zone. Here we call as it is a Fresnel zone. Consider the wavefront A, B, C, D of a monochromatic light perpendicular to the plane of the paper of wavelength lambda propagating in a direction from left to right. Here from left to right, here shown in figure. Let this P be an external point at a distance B from O. Here, this is the point P at a distance B from O, where O is called as the wavefront with respect to point P. With P as a center, we draw the circle having the radius b plus lambda by 2, b plus 2 lambda by 2, b plus 3 lambda by 2, etc. are drawn here. Here first we take the point P at a distance b from the center O. After that we draw the sphere with this different radius. This sphere cut out the circular area of the radii OM1. Here the radius we consider here OM1, OM2. Here we consider OM1, OM2, OM3, OMN. Means in this way we will draw here the number of the circles having the different radius on the wavefront. This circular zone are called as a half period zone. Here that circular zone is called as a half period zone or half period element. Each zone is different from its neighbor. Here every zone is different from its neighboring zone, and the difference in between these two zones is taken as the pi, or phase difference is taken as the lambda by 2. It means that the difference between these two zones is a lambda by 2 or the pi. The area enclosed by the first circle M1 is called as a Fresnel first half period zone, and the area between the n minus 1 circle and nth circle is called as a n half period zone. Here the area enclosed by the first circle M1. Here this is the area enclosed by the first circle is called as the first half period zone, and the area enclosed by the nth circle and n minus 1 circle means its previous circle. Then the area enclosed between these two circles is called as the nth half period zone with respect to the point P. Then find out the radius of this half period zone. For that we consider the Rn be the radius of the nth circle, and we consider the nth circle, and the radius of this nth circle is Rn here, and b plus n lambda by 2 be the distance of the nth half period zone from the point P, and here we consider this distance b plus n lambda by 2 is a distance of point P from the nth half period zone. Then from figure we consider the triangle. Here is the O. We consider the triangle O M N P. Here we consider triangle O M N P. Then by apply the hypotenuse rule. The hypotenuse rule state that the MN P square equal to MN O square plus OP square. Here MN P square is equal to OMN square plus OP square. This MNP is nothing but the B plus n lambda by 2. Therefore we take this value here B n lambda by 2 whole square. OMN is nothing but the radius of the nth half period zone. Therefore we take this value Rn square, and OP is nothing but the distance from the center, which is taken as B. Here we get the B square. Then from this Rn square become B plus n lambda by 2 whole square minus B square. We simply take this value here. Then solve this bracket. We get B square plus 2bn lambda by 2 n lambda by 2 whole square minus B square. This B square get cancelled. The remaining term is a 2bn lambda by 2 n lambda by 2 whole square. Since this lambda is very much less than this B is nothing but the distance between this point P and the center O, and lambda is the wavelength of the waves or the wavelength of the monochromatic source. Here we consider that lambda is always less than that distance B. Therefore the term this lambda square is become neglected. Therefore the remaining term here is only Rn square equal to Bn lambda. Here 2 to get cancelled. The remaining term is only Bn lambda, which is written as Rn equal to under root of Nb lambda. Thus the radius of the first, second and third etc. half period zone are. Only place the value of n, means n equal to 1, 2, 3, 4. Here for 1 we get lambda under root of b lambda, for 2 we get under root 2b lambda, for 3 we get under root of 3b lambda. In this way we get the radius of the nth half period zone. Therefore the radius of half period zone is proportional to this n is the natural numbers, b is the distance of the point P from O, and the lambda is proportional to the square root of the natural numbers and the square root of this lambda. Again this lambda is the wavelength of the monochromatic source, and B is the distance of the screen from the center of this zone. This is nothing but the constant value B. For throughout the experiment, this distance B and the lambda remains constant. Therefore the radius of the half period zone is only depends upon the natural numbers of the depends upon the square root of the natural number. The next is the area of the half period zone. Let An be the area of the nth half period zone. It is bounded by the consecutive n minus nth, n minus 1 nth and the nth circle. Here we have to find the area. Here this area is bounded by nth circle and its previous circle, means n minus 1 circle. Therefore we write here the area of the nth half period zone, means area of the nth circle minus the area of the n minus 1 circle. Therefore we get this radius of nth circle is nothing but the nb lambda, and for radius for the n minus 1 circle is n minus 1 b lambda. After solving we get pi b lambda, means area of the nth half period zone is pi b lambda. This depends on this all constant value. Thus the area of the each half period zone is equal to the pi b lambda. Thus the area is depends on the wavelength, that is the wavelength of the light, and the distance of the point from the wavefront. For every half period zone this area become constant. For every half period zone this value becomes same, because it depends on the constant value pi b lambda. The resultant amplitude at P, let's A1, A2, A3 and so on, represent the amplitude of the vibration of the particles at P due to the secondary waves from the first, second, third and etc. half period zones. Thus A1 is slightly greater than A2, A2 is greater than A3, A3 is greater than A4 and so on. In this way we get the decreasing half period zone. Thus the resultant amplitude at point P at any instant P is given by, here we get A1 minus A2 plus A3 minus A4. Here we get the alternate zone is a negative value. If n is a odd, for that we get A1 minus A2 plus A3 minus A4 and so on. This equation can be written like this: A1 by 2 plus A1 by 2 minus A2 plus A3 by 2 plus A3 by 2. In this way we arrange this equation here. But this A1, here we consider this, A2 is nearly equal to or approximately equal to A1 by 2 plus A3 by 2, because A1, because this A1 is greater than A2, A2 is greater than A3 and A3 is greater than A4. In this way the value goes on decreasing. Therefore, we consider here A2 is approximately equal to A1 by 2 plus A3 by 2. Similarly, A4 is approximately equal to A3 by 2 plus A5 by 2. In this way, we get this all value. If we substitute this value A2, A4, A6 here, then solving we get only this value A1 by 2 plus An by 2, first and final value, if n is odd. And suppose if n is even, then we get this value is subtract here an minus 1 by 2 minus an. If whole wavefront ABCD is unobstructed, the number of half period zone that can be constructed with reference to the point P is infinite. If suppose we consider that point P is at the infinite distance, as the amplitude are gradually diminishing order mn and the n minus 1 tends to 0. Here we consider that point P is at the infinite distance from the center. Therefore, this we here consider that zone amplitude of this zone is goes on decreasing. It means that for nth circle, for the infinite distance, and then consider the nth zone, this become amplitude become completely 0 for infinite distance, and hence here we consider for infinite distance that completely diminish up to the point mn and mn n minus 1. Therefore that tends to 0, and finally we get this amplitude a equal to a1 by 2, and the intensity of this point at this point is nothing but the a square. Therefore it become as intensity equal to a1 square by 4. Thank you.